All right. In theory, everything except for the stuff that's due today that you've handed in has been graded. So that took me a long time. So you're all caught up. I'm all caught up. You're all caught up. This is the last class before the final exam, folks. Next week is the final exam. See, fun flies when you're doing time. So tonight we're going to talk about, we got several things to do tonight. We're going to do graphs. Is the first thing. We're going to talk about what's going to be on the final exam. I'm going to give you the address for you to go to for the teacher evaluations, and I'm going to hand you out an optional homework if you want to do it, for which will give you 2 points on your grade. So I'll hand it out to you. It has to do with graphs. It's actually a pretty cool little thing. So pay attention to. If you pay attention tonight, doing that homework assignment will literally take you half an hour. So pay attention. If you don't pay attention, you'll be scratching your head all week going, I don't get it.
What do you mean when you say 2 points? 2 points of?
2 total points on your grade.
Also 2%?
2% of your total grade. You don't have to do it. I mean, if you got that A locked up, you're good.
2%'s a
But,
lot.
yeah, well, 2% is the difference, you know, it could be between
Milk.
any grade, any two, you know, an A and an A plus, or B and a B minus, or any two next to each other. And I don't curve. I mean, I grade like this, right? So 92.5 and up is an A. 90 to 92.5 is an A minus. 87.5 to 90 is a B plus. 82.5 to 87.5 is B. Sorry. Pretty much like that. That's how I grade. And you know, if you're sitting there and you got that, you got that 87.48, and they go, this person never even opened their mouth once in this class, you're getting that B. But most of you have participated, which is really cool. Some of you have just participated with looks like I don't understand a single thing he's saying, but that's a form of participation too. So, but usually I'll give you, a few. I'll give you a tenth around either side of that kind of thing usually. But yeah, 2 points. 2 points is 2 points. So it's because we've had 4 homework assignments plus the in-class lab, so it's a total of 5 homeworks. So those are each worth 2 points. The optional one I'm going to hand out tonight is worth 2 points. So if you do it, it's 2 points on your grade. So, and like I said, if you pay attention tonight, it should only take you half an hour, 45 minutes to get that done. It's really cool though. So, yeah. Wow, we're at the end of the semester already. I think this one feels weird because the weather's been so hot. I was watching the news this morning. They're going, the rainiest April ever since they started, since the 1870s. 21 or 22 days it rained in April. The previous record was 18. So, rainy. All right, so we talked about trees. You guys should be pretty comfortable with trees at this point in time. And with a tree, you're looking at something that has a root and then leaves and that kind of stuff. But you're limited to the number of things that you can put in it, right? Because it's typically this yes, no, left, right, up, down, why not, that kind of thing. But we get further down and we start thinking, what if we want to have a structure that allows us to have multiple entries and have them be connected to each other? And case in point, think about if you're looking at, some highways or something like that, right? So this, or some city streets or whatever. could have something that looks kind of like this, you know, somewhere in a city or that kind of thing. And you decided, hey, I'm going to write my own GPS or whatever. And you're looking at this going, what kind of a data structure would I be able to use for this if I wanted to, you know, get all my roads and intersections and all this kind of stuff. And then, of course, if you're in Massachusetts, you may even have one of these wacky jobs, right? Something like that. Now, it would be nice if we had some way that we could represent this stuff, because this is more complicated. This one, you know, you're basically looking at best case, you got 3, right? 1 up, 2 down. That's about the best you can do. But any intersection here, like this intersection here, we got 1 here, 1 here, 1 here, 1 there. It's too complex for this. We need some kind of a data structure that's going to allow us to take more complex things like this and represent them. I mean, a lot of what you're doing with data structures is representing something in a form that the computer can digest. That's what you're all about. You're about figuring out, how would I do either of these 2 things with a data structure? Well, enter graphs. That's what graphs are all about. And in graphs, what you would do is you would say, hey, I'll put something here, I'll put something here, I'll put something here, 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 in that case. And what happens is now, we'll call each one of these guys here a vertex. So these are vertices. Etc. You get the picture. The rest of them are also the same. Now, what we do is we connect these vertices. So in this case, it's pretty straightforward to see, hey, this guy's connected to this guy. This guy's connected to this one. This one's connected to this one. This one's connected to that one. That one's connected to that one. That one's connected to that one, et cetera, et cetera. And we could even do this with this, right? Where we have 1 here, and then we have 1, 2, 3, 4, something like that. And we could do something like that. The nice thing about a graph is that vertices can have all these connections to them. These connections are called edges. So what happens is we can have all of these edges connect to a vertex. And if we look at this here and we say, okay, if we drew this as far as the computer was concerned, it would look more like this. Looks like this. And you know, and this is what your GPS is doing. It actually has all of the maps that it has are turned into graphs. And then it uses these graphs because now we can actually say, hey, you know what? These are our roads, right? So this one here is 35 miles per hour. This one here is 45 miles per hour. This one here is 25 miles per hour. But this one's 50, this one's 50, this one's 50, this one's 25. And it can actually go, if I want to get from here to here, what's the quickest way to get there? Your GPS does it all the time, doesn't it? Go, okay. And you can say, well, I want to avoid toll roads or you know that kind of thing, or no interstates, and that kind of stuff. So that becomes this. So this is, you know, I found that I've been, you know, teaching graphs forever, you know, for like 20 years. And a lot of times, a lot of these data structures, you look at them and you go, well, what would I ever do with that? Well, boom, here's something right off the bat. This is what you do with it. This is something you can do with this. Now, graphs, I mean, this is highways. We can also take a look at what happens if we were deciding to start up our own airline. So we got Boston over here. We got Atlanta down here. We got Dallas here. got Denver here, got San Francisco here, got Los Angeles here, that kind of thing. And now you could sit here and go, oh, well, you know, I want to connect from Boston to Atlanta, and then I'm going to connect to Denver, and then from Denver I'm going to connect to Dallas, and then from San Francisco I'm going to go direct to Boston, and like this. And so you start out with something like this. This is pretty easy to represent in a graph, right? We got all these vertices, and we got these edges that connect them. Edges come in two types. There's one that has an implied bidirectionality, and these are called undirected graphs because any path is bidirectional. So this would mean that if you're able to fly from Boston to San Francisco, you're able to fly from San Francisco back to Boston. If you decided it was a one-way thing, which becomes a lot more important here, right? You could say, all right, well, instead of doing that, let's go, you can only go in one direction. And this is called a directed graph. So a directed graph lets you go in this one direction, and we can do that. Now, if you do this, that means there's going to be a lot of traffic in LAX that's never going to get out of there. So you might have to go, well, yeah, let's throw one of these in here, like that. So now you can go from there, and these guys can still be bidirectional. But the minute you make it a directed graph, you're kind of like, you kind of have to go through and make everything directed. So what would happen is, like, from Boston to Atlanta, we can go this way and we can go that way. If we can only go in one direction, like I said, you only put one there. This one, we could go in this direction, and we could go in this direction. So now you have a directed graph, and it does that kind of stuff. And one of the things that I usually talk about is, like, when GPSs first came out, they built graphs inside there. That was basically how they did this stuff, yeah.
So what if we have like a combination of unidirectional and bidirectional? What does the graph
This
called?
does that right now.
So it's still called?
It's still a directed graph. An undirected graph is always bidirectional. If any
all
of them are
edges
not,
bidirectional.
you have to, like, if you look at this here, right, we could say that, hey, you know, like this street here is only in that direction. But, like, these dead end streets, right, these ones kind of have to be bidirectional. Otherwise, you got a lot of traffic coming out or a lot of traffic going in that never comes back out. So when your GPS first started, it was like, okay, let's just do this. And they did this. This is 25 miles an hour, 35 miles an hour, 45 miles an hour, that kind of stuff. Actually, that wasn't first. The first thing was distance. How far is it from point A to point B? So what your GPS was good at doing was, you at a uniform speed, this is the best route to take. And then the next step came along was like, hey, what if we assigned weights to these edges? And in this case, we actually have two of them because there could be a distance component as well as a speed component. And so we can assign values to the edges of our graph and say, this costs this much. So because of this, there are actually a lot of shortest path algorithms based on cost. One we'll talk about tonight is Dijkstra's shortest path algorithm. And so you can build these guys, and so when you first started out, your GPS only did distance. So it couldn't differentiate between a 30-mile-an-hour city road and I-95. As far as it was concerned, they were the same thing. Not very effective. Also took like 20 minutes for everything to get signal too, so but whatever. And then they said, oh, well, why don't we add speed in this? Now you could calculate time as to which one was going to be the fastest. So the cost of an edge doesn't have to be static. It can be dynamic. It can be updated constantly. You could be searching the stuff in a database, pulling this out, and based on the current state of the system, here's what's going on. This is still kind of static, right? I mean, the distance from here to here does not change. And the speed limits might change every so often, you know, every couple of years. They actually changed the road by my house. I'm kind of upset about it because they actually changed the road without doing all of the stuff that they're supposed to. They actually decided to call it thickly settled, but you have to actually have an engineering study done in order to call something that's thickly settled. So my My wife's like, well, why don't you go down to the city hall and talk to them? Sure. You want our taxes to go through the roof? No, I'm good. So, but these are static, right? Distance and miles per hour are static. Might change every so often. They don't add a lot of roads, right? Every now and then, there's been this annoying thing out in my part of the state where they've been converting a lot of intersections to rotaries. And but that
It's
changes.
cheaper.
There were stop signs there before. Now there are yield signs at a rotary. There was no light there or anything. And what's really weird is because the things are so small, the rotaries are actually only this tall. And they have ramps up the side of them because tractor trailers can't go around them, they have to go over them. It's
Yeah,
crazy. Well, their logic is that it slows people down. It's a longish stretch of road. They don't want people going way over the speed limit, so they put
So
these
they have a,
things slow.
what over the rotary?
Well, there's a rotary by my house that goes like this, and it's literally a four-way intersection. And they put a rotary here to slow people down because there's a long stretch from here to here, and they didn't want people going way over the speed limit. So they put a rotary in there so you have to slow down. Cars do this, like that. But this thing is literally from here to that wall is the size of it.
Oh.
So because of that, tractor trailers go down this road and they can't go around this. A tractor trailer is physically not able to go like this, so they basically do that. But they still have to wait to enter the rotary. So the profile of the rotary is, and this is actual size, the profile of the rotary is like this. That's it. And this out here is cement, and then the rest of it's brick. And so tractor trailers have to drive right up over the top of it. But so they put this there to slow cars down, but it really doesn't slow tractor trailers down very much. But I don't know. So static information. Then what ended up happening is we got cameras on the highways. So the overpass on 90, there's a camera that points west, and they look at how much traffic is there and that kind of stuff. So they started adding that stuff into here. So like this one, we might know a delay factor for this one because we know there's a ton of cars there. And that ton of cars is going to slow things down. So we can say that the speed limit here is, we multiply the speed limit times the delay factor. And that would give us that kind of a value. Then Waze comes into the scene, right? Where anybody who's running Waze, you clicked on that I accept this agreement, even though you didn't read it. And that agreement says that they're going to pull your position information from you and share it with everybody else that's there. And that's why Waze, you'll be driving down the road and all of a sudden the road will light up red. Because there are people running Waze that are on there that have slowed down because their GPS information being reported back up to the cloud. So this speed limit is actually now dynamic. So it's dynamic in Waze so that it can actually reroute you if the speed drops too much, that kind of stuff. This is all done with graphs.
I thought people had to report it in ways. Like you would report there's traffic. That's how it started.
That's how it started. Doesn't do it anymore.
Oh,
Good. So, this is a graph. And like I said, they come in two varieties. There's directed and undirected. And the directed ones, each edge has to exist. And in reality, if you wanted to draw something with bidirectionality, you can do this, and it kind of makes it. And part of the reason why you do this is because there are actually situations where in this direction, you're allowed to go 25 miles per hour, but in this direction, you're allowed to go 30 miles per hour. And they do that.
So this is still a directed graph?
Yep. Anytime there's an arrowhead, it's a directed graph.
We are using street cameras in there.
Well, they used to use them, but now they have better information through Waze. And then Google Maps does it too, and Google owns Waze, so.
Isn't
Imagine
Google
that.
Maps the same as Waze now?
Huh?
Shouldn't Google Maps be the same as Waze?
Well, part of the problem is that you had these two separate companies that started up and have separate ways of doing things. Right now, they're not. Eventually, they will merge. And that's...
I've always wondered why they give you different data if you're owned by each
Yeah,
other.
because they have different databases and different
Uh.
stuff like that, different ways of reporting it, different protocols, different all that kind of stuff. Over time, they'll merge together. So, questions on what they are?
Wait, this the difference between directed and undirected again is undirected. It's one way.
Undirected, it's bidirectional. All paths are bidirectional.
Oh, so directed is.
Directed is whatever direction the arrow tells you goes in. So
It's
this
a directed follow
this
the
is
arrow.
directed.
That's directed.
And if we looked at the same one undirected, it would just look like this.
Okay, so one has arrows, one doesn't.
Yep. All right. They're kind of cool. Hopefully you're sitting there going, hey, you know, I was thinking that, let's see, printed circuit board layout. Boom, graphs. Here's all the parts. Here's all the connections. Let's hook them all together. We got these buses that need to connect to each other. We need all this kind of stuff to do. Bus routes. Boom. Crowd control at an amusement park. Boom. All this stuff. Anything that, you know, you can take a look at. Let's, think about it, an amusement park. So if you have this brand new roller coaster that opens up, but the sidewalks aren't big enough. So you can actually run simulations with a graph to say, if the cost of getting here or the number of people that could get through per hour was this, we put that cost on one of the edges and you can actually simulate an amusement park this way. So these things are really, really powerful because we've now gone past the 1-to-1 or 1-to-2 type things. And when you're developing software, there are 3 things you have to worry about. There's 1, there's 2, and there's n. So 1 to 2 is actually a relatively easy jump. 2 to n is much more complicated. And this is n. We've done 1 to 2. We did 1 with a linked list. We did 2 with a tree. Now we're at n. And so we can have n connections, n costs, and all kinds of stuff.
In this simulation, it's saying the edges have weight. Is there any situation where the vertex will have weight, where it's saying, hey, you can do this, but then you'd have to go through, I don't know, a border crossing, and that's going to take so long, or does that get
what you would
put out
do
on
in
the
that
edges?
case is you would actually have something that goes like this, right? From here, then you'd have, here's your border crossing, and away you go. So typically, the vertices don't have that kind of stuff, and
It's
there's-
just placed onto the edges?
Yeah, it's placed,
Okay.
all the responsibility is placed on the edges. Now, if we take a look at another thing, which is, this one happens very frequently in software. And one of the things that graphs are used a lot for in software is a thing called how many people have ever heard of a state machine?
Everyone's raising their hands.
Yeah.
I'm screaming out.
I just didn't want to ask you.
I don't know I'm gonna tell you what it is. Basically, what happens is you start in some state, and then something happens, and you transition to another state.
Oh, that's.
Something happens, you transition to another state. You've seen these kinds of things, right?
Yeah.
One of the things, sometimes these things start out as software, get pushed down to hardware. So there are state machines all over in your processors, the architecture, all that kind of stuff. Complex software is frequently written as a state machine. So what happens is video games are written as a state machine. So if you think about this, right? So let's say that we are playing some video game, all right? And we've come across a door. And in this door, we want to open the door. So here's our current state. Here's our next state, which is this is door closed. This is door open. Now what we can do is, if you don't have the key, if you don't have the bag of magic stones, if you don't have whatever, you can't get from this state to that state. This happens all the time in software. Large, complex games are written as state machines. because it's very easy for you to keep track of all of the things you need in order to get there. So there will be a cost function that's associated with transitioning from this state to this state, but it's still a graph. This is a vertex, this is an edge, this is another vertex. Does that kind of stuff. One of the things that when I took switching theory and logic design, I was working on my master's in electrical engineering. We had to come up with a binary synchronous state machine. The whole purpose of it was to read codes of strings of binary digits. So maybe we have some packet that starts with a string of code, looks like a Jeep front end, you know. Okay, no, sorry. It starts with a 1 followed by a bunch of zeros, and then after that is some amount of data, and it could be, you know, 1s, 0s, 0s, 1s, whatever, and then it ends with the same 0. So we're gonna realize that our data transmission starts here and our data transmission ends there. So what happens is you have a simple state machine. The state machine's whole purpose in life is read zeros, read ones, read whatever. So you start here, and what happens is you're in state 0. And then what happens? This is where we start. Ta-da! A 0 comes in. Cool. On a 0, we go to state 1. So this is on a 0. On a 1, we just stay back in this state because we're scanning through till we hit this 0. Then we're looking for a 1 after it. So once we hit the 0, then we're good. Then if we get another 0 after that, we come back to this one. Right? Now, so that means we get from 0, and then what happens after that? If we get a 1, that takes us to state 2. Right? And then after here, if we get a 0, we go back here. Now here, on another 1, we'll come over to state 3, but on a 0, we'll go back to here. And so now what do we got? 0, 1, 1, need 2 more 1s. So this is going to be on a 1, this is going to be on a 1, and then lastly we'll have one come on a 0, which takes us to state 6. Now, any of these, the 1s take us in the right directions, the 0s all take us back here. On that one, on this one, and then once we reach here, we've actually finished up the point where we're good to go. We now have read this magic marker that tells us data is about to start. It's a state machine. It's also a graph. And these work a lot in low-level systems. Your whole operating system is basically a state machine. What does your task do? It goes from dead to alive to running to delayed to paused to dead. It's a state machine. The whole thing's running in a state machine. Complex software is built around a lot of this stuff. That's why graphs are so important. And they're just freaking cool. They're not as cool as freaking laser beams, but they're pretty cool. Now, let's talk about implementations of graphs. I mean, I'm sure that you guys could figure out, even after this half an hour that we spent talking about them, that there's a lot of applications for this stuff. I mean, you could use these things anywhere, but you got to be able to implement them. Typically, there are 2 forms of implementation. There's something called an adjacency matrix and something called edge lists, but they're also sometimes called edge sets, which I think sets is the wrong term, but somehow, because some languages have sets as a data type. So we call them edge sets because that's built into the language. So what happens here is, so I'm going to go out on a limb and say one of these is probably array-based and the other one is probably linked list-based. What do you think? Think I'd be that far off?
Ding, 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 ding.
Yeah, ding, 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 yeah. Winner, winner, chicken dinner. So, matrix. array. List. Linked list. Yep. This is pretty straightforward. It looks like this. It looks like this. Now, if we want to do an undirected graph, you kind of only need half of it, right? Because each connection would be implied. If we decided that, hey, you know what? There's a connection from V0 to V1. Just put a true there. We decided there's a connection from V2 to V1 and V3 and V4. And V3 can connect to V0 and it can connect to V2, and V4 can connect to V3 and V0, and V1 can connect to V2. So, just using trues and false, right? So it's a Boolean array, right? It's kind of like a two-dimensional Boolean array, and it's a complete implementation of a graph. This everything you need. And you know, you can even use the indexes. So, needless to say, getting around this thing is quick because it's simply array math. And that works pretty good. Based on this, if we draw this, we end up with V0, V1, V2, V3, and V4. Here's what we have. There are 4 vertices in here. According to this, V0 can connect to V1. V1 can connect to V2. V2 can connect to V1. It can also connect to V3. It can connect to V4. V3 can connect to V0 and V2. And V4 can connect to V0 and it can connect to V3. Ta-da! Pretty straightforward. That one's easy. It's kind of weird. I mean, when we started out on this odyssey of data structures, we started playing with general purpose linked lists, which are a bear. You got to worry about inserting in the middle, you got to insert at the side, you got to insert at the end, you got to insert whatever, blah, 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 blah. We get up to this point in time, everything's been kind of just that pared down to get us to something that works. So that one is that graph and that adjacency matrix are the same. And what we would do then with the ones that aren't here is false, false, false.
That's the bonus square.
So here's an adjacency matrix representation of that guy. Now, what do you think are some of the plus sides to an adjacency matrix?
Fast.
It's fast. It's simply an array, right? Downsides?
Limited space.
Not
Defined-
limited,
well,
but
it's defined. It's like,
yeah, it's
you-
expandability.
yeah,
is-
that's the better word. It's like
Yeah.
once you go
Yeah.
one over, you're screwed.
Yeah, once you want to add a new vertex to it, it's stuff. That kind of thing. It's pretty much standard with every other data structure we've looked at. You do an array-based implementation of a queue. And, you know, once you want it to grow, you're in trouble. So, one of the huge benefits of this guy is random access. And you can get to any vertex just by knowing what vertex you want to get to. Now, if we look at that and say, okay, so now we're going to do an implementation of this graph, but we're going to do it with linked lists, basically. So this one gets complicated because there's a lot of different weird things you can do with it. We could start with a structure that looks like this. And this could be vertices, right? So this would be V0, this would be V1, V2, V3, and then you need a V4.
Would V1 be the data within the node, or would it be something where the node is labeled V1 and stores data of all the vertices it has access to?
Well, there could be something in there. Say that inside of this, say that these are roads, and inside here are the number of cars that went by each day, or whatever.
Okay.
You know, that kind of thing. There could be whatever you want it to be inside here. So this is one way to do it, and this way is actually kind of complicated, and we'll see why in a couple seconds. One of the things that's a problem with this is that this is a data structure, but these data structures also have, off this end,
So is this a variant of a doubly linked list?
what's that?
Is this a variant of a doubly linked list?
Yeah, those ones are, but these ones out here will just be regular singly linked lists. So what we would do now is V0, and if we look there, V0 can connect to V1. So we'd have a V1 here. And then we'd go like that, and V0 can connect just to V1, right? So because of that, then this would go like that. V1 could connect to just V2. V2 can connect to 1, 3, and 4. V3 can connect to 0 and 2. And V4 can connect to 0 and 3.
Is this a visual representation of a multi-dimensional linked list?
Kinda. Yeah, I guess you could say that. Now this is one implementation of this as an edge list. Now, what's kind of weird with this is that typically if you're going this route, you're gonna go for broke. Because what we could have done is instead of this being a linked list here, we could have just did this, right? This could have been an array, right? An array, and then these guys would then, you know, refer to that guy, et cetera, et cetera. But here we went with a linked list here. Now, if we did go with the array version of this, what's nice is that we can go, hey, we get out here, it goes to V1. Okay, so we'll just go to the 1 here, which takes us to the here, and then we can do that kind of stuff. The problem is if we get out here and we go, oh, we want to go to 3, now we got to go back to the top here and work our way down to 3, which is really kind of slow. So what typically will happen if you're taking this route, and this is the only truly extensible version, right? Because if we do this one, we have to, that's an array. Once that's done, if we want to add more vertices, we have to increase the size of that array. This one, these are dynamic, we can just add them as we need. But in order to climb through something, like say you want to take the path from V4 to V0 to V1 to V2. So here we go, from V4 to V0 to V1 to V2, done. This one here, we go from V4 to 0. We have to climb up down here, go V0 to V1, climb back up here, come down to V1 to V2, climb back down here to V2, right? If this was an array of these, we could go V4 to 0, 0 to 1, 1 to 2, and we're done. So if we run this one, which people do, I mean, if your number of vertices is frequently changing and all that kind of stuff, you'll run this one where this is actually a linked list in that direction, plus this. These guys then become doubly linked lists too. And what happens is V1, for example, would be there, but there would also be this. This V2 would go like that, but it would also go to here. This one here would go back up to there. This one here would go down to there. This one here would go down to there.
That's a lot of overhead.
There is, but the speed benefit's amazing. Because what happens if you have 500 vertices? If you have 500 vertices and you have to go back to the beginning of this list and count through them each time in order to get there, that's a problem. That's going to slow you way down. Whereas this one, once you get to here, it knows where the next vertex is in the chain. Make sense? Yeah.
For doubly linked lists, for example, with vertex 2, it points to several other vertices. So how would it sort of account for that in?
Well, right here you have this one would go to there, then that one goes to there, and that one goes to there. So you still have a linearity and you're going across these things like this. So this is big O of n this way, but then it's instantaneous down to where you need to go next.
Okay.
Without those, then what happens is it ends up being big O of n for here plus big O of n for there. And if this number is huge, it gets to be really big. So what you will typically see are the extremes. You'll either see somebody will go with the array-based vertex list, and then off of that, the edge list will be a linked list, or they'll go fully connected. Very rarely do you see the one that has these being these and these not being connected to. So what we'll play around with mostly is if the vertex list was an array, because it's easiest. But I wanted you to understand that you can build it this way. It gets pretty complicated. Plus, if you forget the dot one I or cross one T, you can destroy the entire graph. Which is not a place you want to be. If you have a fixed number of vertices and they're not going to change, or they're not going to change that often, this is by far the best way to go. Questions? Okay, so we've talked about what you can do with them. We've looked at them architecturally. I mean, the next thing to do is see what they look like in
Any
code.
questions from guys on Python?
Of course there will be. No, we're gonna completely skip the class that has all this stuff in it, and it won't be on the final at all.
You'd
Said
only know that if
nobody
you came to
ever.
class. But you would only know that if you came to class.
Huh?
You would only know that if you came to class.
Maybe. You never know. Final's already done. I know what's on it. Yes, this stuff's on it.
All right. So let's go with the adjacency matrix first, because it's by far the easier one to implement. And there's a set number of functions that are associated with a graph. And you know, before we do the implementation, let's look at traversals. You know what? Let's do the implementation first, then we'll do the traversals. Once we have them implemented, we'll take a look at the traversals. Because just like there are traversals for binary trees, there are traversals for graphs. And in this case, there are breadth first and depth first traversals. So we'll take a look at those once we get the implementation done. You know what? Why don't we give you 5 right now? Come back and we'll pick up and run from there.